Okay. We are on YouTube.
Okay. So I hope everybody is around. And yes, so let me start again. So this is the last video. Okay, the second session of day 5 and the final one. And I will start discussing new kinds of types, which are called higher inductive types. And we will see 2 of them, okay? And of course, there are many more. We will see the circle, and we will see the suspension of a type. Okay, so let me first define it and then try to comment on why it is called the higher inductive type. Okay, so the idea of the circle, the idea of the type theoretic version of the circle is very graphical, okay? And as we discussed sort of offline just during the break, it is a very combinatorial way of saying things. So in order to get a circle, what you need is a point, okay? So it's one data, and then you need a loop around this point, and this is your second data. Okay, so that's the idea. And here, this is accounted for in the 2 first items. So first we declare a new type, which we call S1. Okay, so S1 stands for one sphere. So this is a sphere of dimension 1. And the 2, so we postulate that there are 2 constructors. One is a traditional one, so we say that S1 has 1 inhabitant, and this one is not traditional. Okay, this is what justifies the adjective higher inductive types. We postulate another constructor which is not of type S1, which is of the equality type over S1. So we define the type taking into account its equality type at the same time. So it's something new. I mean, it's certainly not the case with natural numbers. So this justifies the fact that this is a special sort of new types. And as a matter of fact, I don't think higher inductive types were sort of started to flourish about 10 years ago or a bit less. And up to now, I don't think that there is a single paper that gives a general theory of a general definition and a general theory of higher inductive types. There are some attempts. There is a paper by Cocan and others, or students of Cocan, I don't remember. But anyway, so let's keep this a bit intuitive, okay? What is really the notion of higher inductive type? Just be aware that here something new happens, okay? And then we have an induction principle. Okay, so the induction principle is a bit hard to read. Okay, so let me try to do it slowly. So it starts as usual. We want to find a way to define functions out of the circle. Okay, so we start with a type family that depends on the circle, P from S1 to U, and we want to have a tool to define a function in this type. So Px whose domain is S1 and whose codomain is this dependent, well, this dependent type Px. Okay, so in order to define it, what I need, the induction principle tells me that all what I need is to have a point in P of base, okay, the idea is that, of course, I want to draw a circle I want to draw a circle here. That's because to map a circle into somewhere means I want a circle. So I need a point, okay, and I also need a loop, okay, around this point. So you see my convention. Base is the point is in S1, and little b is a point in P of base, okay. And I want a circle, so I want a path, okay, around B, okay. So why do I want this? So maybe the best is to look at the picture, which is here. So the picture is copied from the hot book. From the data of B, only B, okay, and from the data that I have this type family P, okay, and the fact that I have a loop in S1, I can get some path in my surface, okay, which is the image of loop by the family. So no, maybe I'm not very clear here. Okay, so let me read this picture in another way. So yeah, okay, sorry. What I can do with this point B, because I have this type family, I can transport it, okay, along. So I can transport, yes, this B along loop relative to the family P, and then I get another element of P of base, okay, because loop goes from B to B. No, sorry, no. Loop goes from loop is of type O. I don't need to write it again. It's here. Loop is a path from base to base. Hence, transporting B along loop gives me another point of P of base. So you see, I have my B here, and then I have this transport. Loop star is another word for transport loop B. I have a point here, okay. And what I want is, this is what I require. I want a path from between these 2 points. And intuitively, that's where the intuition lies, is that by the magic of transport, this loop is reflected in my space. So here it's a bit confusing because P here you have to think of this as the total space of P, because it's just one space. So this picture is more like representing sigma xs1 px. Okay, so this loop gets mapped into some path in the total space, but I'm not guaranteed to have that this path is a loop. And what I want is actually to have a circle in here. I want to have a circle here. Hence, I require the existence of the path here, which sort of gives a missing part, which is to make sure that I can go from this transported point to B by a path. And the two together will give me a path in the total space. And hence, I will have a circle. Okay, so this is more or less clear explanation of what we need. But now let's be formal. And formally, okay, the induction principle asks for a point in P of base and a proof that transporting B along loop relative to P is equal to B. Okay, and what are the associated equalities? First, that if we apply this function to B, the function that we just produced, applying it to base, sorry, should return the point that we have chosen. Okay, so that's quite obvious. And the second thing is that if we apply this function to loop, if we apply this function, yes, if we how to read this? Yes, so yes, if we apply this function that we just obtained, if we apply it to loop, okay, what we should get is precisely the L that we provided here, okay? And this should be propositional. So it just says that, morally speaking, it just says that the function that I just produced takes the loop to this path. Okay, because this is the only thing that you can say in a dependent setting. In a dependent setting, you cannot say that it returns a proof that B equals B, because you have transport involved. Okay, so another way to say this is that there is a notation in the hot book which is probably more intuitive, but I don't use it. Is that this kind of equalities is written B equals B, something like loop or something like that. So up to transport by the loop, B is equal to B. This is more intuitive notation in the sense that it records us, it reminds us that this is the version of a path from B to B that takes into account the fact that we have a type family and that we have transport involved. Okay, so then that's okay. And to relax a little bit, the principle, if I don't want the induction principle, but I just want a recursion principle, then it's simpler. Okay, so maybe I should have started with it. So let me start over again and just define recursion. Okay, so remember the difference between recursion and induction is that in recursion, I don't look at a dependent family, but I just look at the type. So I just want to define a function from S1 to A and not a dependent function. And then the recursion principle is easy to read. If I want to have a function from S1 to A, what I need is a point in A, and a loop around this point in A. Okay, so I want a circle that sits in A. And then I have my official circle here. This is S1. Okay, I have my official circle here, that's S1, and I have my space A here. And I just want to draw a circle inside this A. This is A. And for this, I need a point in A, and I need a loop around this point in A. And this is exactly what is written here. And it's easier to remember. And then the associated equalities are also easier to read. Okay, now little point is that this recursion principle is derived from the induction principle. So the induction principle is more general, and you can infer, so you don't need to specify both. This one can be inferred, But the proof is, well, it's not, you need to do something to prove it. And you may remember from an earlier lecture that I discussed that there are differences between app and appd. Okay, app is a functor, and this is a dependent variation on functor. And I showed to you that in order to compare them, you need to do a little bit of work and to introduce some transport between the two. And you see that this transport has to reappear. If we are here, there is no transport involved. Here, if we are here, there is transport involved. So you have to let it reappear in some sense. And so the proof that rec S1 is derived from int S1 is very much in the same style that app and appd can be related with each other. Okay, and another thing here, which I will use, okay, and I think this matches some comments that were made on Discord on some exercise, I think, I don't remember which one, namely the fact that in this recursion principle, I do not insist U to be the first universe. So far we never really cared, because we managed somehow to live always in U0. But here I will actually need to use the recursion principle with U instead in place of A. And then, okay, and then if here I have U, then here I have U1. Okay, so I need this recursion principle to hold not only for U0, but also for U1, and more generally for actually for any UI. Okay, so I will assume this recursion principle even if U is not the first universe. Good. Okay, so now we need another ingredient, because remember that our goal is to show this theorem here, which I predicted in the plan of the lecture. We will want to show that the equality type base equals base in S1 is equivalent to the type of integers. Okay, so maybe before I define integers, I can give you an intuition. Well, the intuition is that it's again combinatorial, because S1, in S1, what are my tools to build a path from base to base? Well, I can use the reflexivity. I can use also the path loop, which is provided in the definition. Okay, so I can use either reflexivity or I can use loop. But I can do loop concatenated with loop. I can do loop -1, and I can do loop loop concatenated with loop n times, and I can n times for n natural number. But because I have also the inverse, I can also do loop -1 concatenated with loop -1. Etc. So I can do also loop -n. So you see that I can do loop any integer number of times. And what this theorem says is that this is all what there is. So the type of paths in base equal base is equivalent to the type of integers. Okay, so now we have a motivation to define integers. And here I use a definition which, so you have different ways to define the integers. And here we'll use a definition which I found in the note of Hugo Munn-Clay. So I mentioned this in the first slide. This is my second reference besides the hot book. So here's his definition, which I find nice. So essentially, he defines the integers as being somehow the disjoint union of one copy of n. That's for all strictly positive numbers. Another copy of n, that's for all strictly negative numbers. And then in the middle, he puts one element, which is 0. Okay. So in order to make this more intuitive, he first defines a kind of copy of n, which is defined exactly like n. So he calls it n plus. Okay. And n plus is defined exactly in the same way, except that the constructor 0 is now named 1. Okay, so it is just to keep in mind that everything starts at 1. So you have 1, success of 1, success of 1, etc. Okay, so now we can define the integers as an inductive type, which is not higher. Okay, so let's define it. We have a type. We have constructors. So you have a 0. Okay, and we are provided with two functions. So if we know a strictly positive number, then we can insert it in Z in this way, and then we will call it plus n. Or we can insert it in Z in this way, and then we will call it minus n. Okay. And the induction principle tells you essentially that these are the three only ways to get an integer. So if we want to find a function out of Z, so a function here, okay, with the type family depending on Z, all what you have to do is to find an element in C0, okay, that will be the image of 0. You will need a function from n plus to C of plus x. So that's defining the function on all strictly positive numbers. And you will also define a function from n plus to dependent function that maps each x of n plus to C of minus x. And that will define the restriction of the function to the strictly negative numbers. So with all these data, one element, one function, another function, I get a full function out of Z. Okay. And I forgot to write the definitional laws, but they are obvious. Okay, maybe I write them now. So of course you want that int Z applied to C applied to some element in C0, let's call it C0, some function f and some function g, okay? You want that when it is applied to 0, it returns C0. And what you want is that the same thing, okay, so here I don't repeat, okay? You want that when it is applied to f, when it is applied to plus, yes, when it is applied to some element of the form plus n, then it returns f applied to n. And when it is applied to minus n, then it returns g applied to n. Okay, and all this is definition. Okay, so this is the induction principle. And we can apply induction to define two interesting functions. One function from Z to Z, it is the function plus 1. And one function from Z to the type of loops or, around the base, which is a function which maps Z to loop Z. I already gave you the intuition of loop Z. So it's loop n Z times. Okay, so now I don't provide the explicit definitions, but just do it naively, okay, as we would do in an ordinary way in a logic-oriented textbook. So how can I define Z plus 1? Well, by cases. Okay, so if it's 0, then it's 1. if it's now I have to define it on the strictly positive numbers. So the first strictly positive number is 1, so I define it for 1. So plus 1 is, of course, 2, which is plus of successor 1. And then I have to define it when it is sux n. So plus of sux n is, well, you see that you have to do sux of n. Now, if it is on the negative side, the first element is 1. Okay, so minus 1 plus 1 is defined to be 0. And if it is successor of n, it's going to be n, because on the negative side, of course, minus, here I'm really doing very elementary mathematics, minus n plus 1 plus 1, if I'm not mistaken, is the same as minus 1, minus n. Okay. And for the loop, it's the same idea. Okay, so you say that loop 0 is a reflexivity, loop plus 1 is loop, loop plus sux n is loop plus n concatenated with loop, loop minus 1 is the inverse of loop. So you see that the notation was well chosen, because this is inverse here. Okay, so in principle, these are two different things. This is inverse, and this is a special case of the function that I'm precisely defining. And then loop minus successor of n is doing the same thing as here, but with loop minus 1 instead. Okay, so here we are now approaching our theorem, which is to prove the equivalence between the type of integers and this type, which is also called the first homotopy group of the one sphere. So the mathematical name for this guy is pi1 of S1 by definition. Okay, it's written here, so I don't need to. Okay, so in order to prove this theorem, we shall use the encode-decode method. And just as we made in the case of the analysis of coproduct, we need to generalize this statement in order to let something variable appear. Okay, so we are going to prove a more general statement. Instead of this statement, we are going to prove this statement here. Okay, so we make the problem is that here the 2 points are fixed, and there's no way to do any kind of path induction if they are both fixed. Remember, path induction works if at least one of the endpoints can vary. So we need to replace this type with a type that will be variable on one side. So we choose the right side, and then we will have tools to work on it. But of course, if we change this type, we also need to change this type and to make it also a dependent type. So we need to find a new type, S1 of x, which is such so that will depend on x, which is itself a variable element in S1. And we are going to define it by induction or by recursion, by the way, by recursion. So of course, because we want this to be a special case, we will require that S1 applied to base. Here the font is not good, so I will repair that. Let me just put a note here. I need to put the right font. So we want that S1 of base BZ, so that this instantiates to this, which is our theorem. This is a more general statement, but Nobody wants to remember this statement. Everybody wants to remember this one. Okay, so I have a clue on how to define this S1. So in order to define it now, what I need to do is to provide a value for S1, but here the specification is that I should take Z. Okay, so I should pick, in order to apply recursion, I should pick a B. I should pick a B in A. Okay, so yes. Yes, okay, sorry. This is a general recursion principle, okay, and I'm instantiating it. So this is just copied from the previous slide, where I already anticipated that I need to go to universe 1, okay, and I'm now instantiating this to my situation, and my situation here is to take A equals U0, okay, because I want to find the type family S1 into U, okay. For me, U is U0. So I want to find a type family here, S1 to U, okay. And for this, the recursion principle tells me that I need to find a B in U, and this B is going to be Z, okay, because Z is a type, okay, so it's member of U. And I need also to find a proof that Z is equal to Z, okay. And for this, and here I'm doing univalent mathematics. For this, I will use the function lambda z plus 1. And here there's a missing part in my slides. I should have stated an auxiliary theorem, which I'm stating now. It can be proved that lambda z plus 1, which is a function from z to z, it can be proved that it is an equivalence. An equivalence. And the idea, of course, is that it has an inverse, and this inverse is lambda z dot z minus 1. Okay. So this very, very elementary computations show you that these functions are inverse. And hence, you know that it is an equivalence. Hence, you can apply the univalence axiom and get from this function a proof that z is equal to z, which is a perfect candidate for being the person to put here. Okay. Hence, I can define my family S1 to be rec S1 applied to U0, this is my type A, then applied to a pair formed by Z and by UA of lambda Z, Z plus 1. Okay, so this is my official definition of S1. And now we have to work to find out why this equivalence holds. And then our theorem will be proved. Okay, so before we do that, I will need some auxiliary properties. So let me go through this slide. Yes, so I want to show this property, which I explain now. So given a type family B, given a proof that X is equal to Y in A, I can define transport along P with respect to B, which is a function from Bx to By by definition. Okay, so this is a function from Bx to By. But there's another way to get a function from Bx to By. Namely, I can use B as a functor. It's a non-dependent function here from A to U. So I can use app, okay, app B, which means that I can map by B my path P, okay, to what? Well, to a path. So the P being a path from X to Y, up BP here is a path from BX to BY. And then I can do id to xz to turn it into a function. And this property asserts that they are equal. Okay, so this is very easy. Path induction. So we just need to do this for P, which is reflexivity. And then we see that on the left-hand side, we get the identity because transporting along the reflexivity is the identity. And on the right, applying the reflexivity gives the reflexivity. So we get the, and moreover, taking e to xz of the reflexivity returns me the identity. So on both sides, I have the identity, and this is okay, even definitionally. Okay, but this is definitionally for the case that the P is ref, but of course, induction will just provide me with a propositional equality. Okay, so I have this property, and why is it useful? Well, let's see. So I apply this general property to the case where my family is S1 and my P is the loop, okay? Because loop is a path in A. Loop is XS1 is a family from S1 to U, okay? And loop is a path in S1. So just by instantiating, I get that the transport along XS1 of loop, no, transport relative to XS1 along loop is, well, just instantiate id to xv of app, then XS1 instead of B and loop instead of P, okay? But app XS1 of loop, we already know what it is. It's written here. By definition of XS1 and the equation associated with recursion, we know that this guy is UA of lambda Z, Z plus 1. So I can replace it with lambda Z, Z plus 1. But here I have e to xz of UA of blah, blah. Hence, by univalence, this is lambda Z, Z plus 1. Okay, so we have proved this property. And if we apply it to some Z, okay, then we get this equality here, which we shall use later on. Okay, so this is the first interesting property that is important for us, that transporting any element of Z along loop relative to the family S1 gives me Z plus 1. So you see that the counterpart of loop in the world of S1 is the successor function in the world of Z. That's what this says. Okay, so we shall need this at some point. Okay, so now here let's remind ourselves that our goal is to define an equivalence between these two types. So this type I could as well have called it instead of S1, I could have imitated the terminology used for the coproduct type, and I could have called it code of X. Okay, because this is a way to, this is a kind of code. Okay, it's a trick. Nobody wants to remember this S1, so it's a kind of code, and this is the real thing that we want. Okay, and then we need to encode in this code and then decode from this code. Okay, so let's do this. We need to define encode and decode. Okay, so encode X will be a function from base equal X to S1X. And this one is easy because we can use path induction. So we only need to define it when X is equal to base. And when this is reflexivity. So we only need to do this, to define this. And in this case, we decided to map it to 0. Okay, so it's a decision, which is in S1 of base, because X is, yes, we instantiated with base. So S1 of base is Z, and we give the value 0. And then all the rest is followed by a path induction. For decode, the definition is a bit more difficult. So I tried to do it, to synthesize it. So I want to define a function. Decode is a function, a dependent function, that takes an X in S1 and returns a function from S1 of X to base equal X. And this one is going to be defined by induction on S1. Okay, so what I need to produce, it's going to be induction or not recursion on S1. Okay, so I first need to tell which type family I will use. So the type family which I want to use is, it's obvious, it's this one, because I want to define a function of this type. So I do not have any choice. I need to take this type family. Okay, so it's the same, exactly the same code, replacing pi x by lambda x. And what I remark here is that for this type family, P of base is equal to Z arrow base equal base, because S1 of base is the same thing as Z. Okay, so I will use this. So now what we need is to find here a guy which has this type here. So we need to find a B in P of base, and then a proof that transporting B along loop is equal to B in P of base. Okay, so we need a pair, because this guy is going to be a pair. We need, so box is a pair of box 1 and box 2. Box 1 will be an element of P of base, and box 2 will be a proof of this equality. Okay, so for box 1, we decide to choose the following function, okay, which we already defined. So it has to be a function from Z to base equal base, and this is a function that takes an integer and return loop made Z times. Okay, so this is this function loop Z, loop power Z, loop to the Z, let's say. Okay, so I have my box 1, and boom, boom, boom. Okay, so by definition, we know that decode my decode by definition, because it's this guy, when applied to base, will be this function, because this is we are defining a function which whose value on B is precisely this function, whose value on base, sorry, is this function. Okay, so this is by definition of induction. Well, this is a consequence of induction. So now we need to define this box 2. So we need to find an element here. But for this, we need to understand what is transport along this family. Okay. So this is my family. Okay. And okay. Yes. So I need to analyze this transport here. But this family P is of a familiar kind. I mean, it's a family of arrow types. Okay. And we had an exercise which I commented on. I didn't correct it, but I commented on it, which says that in this case, transport along the family P can be expressed in terms of transport along those types, the family of those types on one hand, and the family of those types on the other hand. So we can decompose transport exactly like this. Okay, so to transport relative to P can be expressed in terms of these simpler transports. Okay. Now we want a formula for this guy. Okay, so we want a formula for in the case where we have loop and where we have lambda z loop z. Okay, so we want to go inside this expression in the case where P is loop and F is lambda z loop z, and see what we can what we reach. Okay, so let's do this. Okay, so we first observed something. Remember that we proved this property here. Okay, so a variant of the same proof would show that if I put here a loop -1, here the result would be z -1. Okay, it's not difficult to think that such a thing can hold, and you can prove it exactly in the same way. So, okay, so we will use this. We will use this auxiliary result here. Okay, so now we have to do a little bit of work. So we know that transport. So this is what we want to compute. We want to know what this guy is. Okay, and we use this formula. Okay, so we get here. This is this formula instantiated with what we want. Okay, and then what we observe is that yes, so here I already integrated the z -1. Yes, okay, okay. So this guy is the same as this guy instantiated in the proper way. Okay, but instantiated in the proper way means that this expression here, when it is instantiated, is exactly this expression here. So this expression here becomes z -1. Okay, so then the rest of the expression is here, because I have not yet computed it. The rest of the expression is here, but it's applied to z -1. Okay, but okay. What I see is that when I apply, so here probably there are little parentheses missing here. So this here is parentheses like parenthesized like this. We see that applying loop z to this function to z -1 gives me loop z -1. Okay. So we have to apply this transport. So now we are here. But this is familiar. This family, we know it already. We know that it is just a matter of concatenating. So I'm concatenating now loop z -1 with loop, and I get loop z. Okay, so what have we done? We have found out that transport P loop lambda Z loop Z is lambda Z loop Z. Okay, then the transport, essentially the transport does nothing. Okay, but this is exactly what we needed in order to complete our definition of decode. Because for decode, we were missing a proof that transport P loop box 1, which is this function, is box 1, which is this function. And this is exactly what we have proved here. So we have completed the definition of decode. And hence, we have our two functions. And what is left is to show that they are quasi-inverses. Okay, so one direction is obvious by path induction. So I'm not going to detail it. Okay, it's just by path induction, you instantiate things and then you do the obvious manipulations. There's nothing to say. The other direction is more interesting. The other direction is to show encode of decode xq is equal to q for q in s1 of x relative. Okay, so we are going to do an induction on S1, and our type family for this will be tailored to this problem. So it is this family here. And in order to prove the equality, I will use two properties. The first property is that Z is a set. Something that I'm not going to prove here, but as I told you, it can be proved that N is a set by the encode-decode method and that Z is a set by the encode-decode method. So here we will admit this. And the second property that I will need is this one. That encode applied to base applied to loop Z is equal to Z for all integer. Okay, so let me check. Yes, okay. Okay, so in this slide, I will show you why these two properties are enough to prove that encode is left inverse to decode. Encode X is left inverse of decode X. And for this, yes, for this, we want to produce a dependent function that takes well, that goes into this type. Okay, so for this we need to find. So this is my type family for tailored to exactly this problem. So I need to find an element in P of base for this P, because then and then a proof that this holds. Okay, but what is P of base for this P? It is this type here. Okay. Because remember that when X is base, S1 of base is Z. So here it's just this type instantiated. Now, instead of having a Q, I have a Z, but otherwise it's exactly the same. Okay. Yes. Okay, and here comes a slight relief. Okay, is that what we need to produce is an element in this type, okay, which is a pair of an element in this type. So we don't know it yet, but something that we already know is that a guy in this type will come for free. Why? Because, okay, so P of base is a function type. but I can prove it. I can prove this equality pointwise. So to prove this equality for each z, okay, will be done. Yes, so I will need to prove the equality between these two terms in this type. Okay, but this type, which is here, is an equality type over z. Okay, so here I have a z. But because z is a set, proving that two elements are equal in an equality type over z, because z is a set, it means that this type is a proposition, and hence this comes for free. So I don't need to care about this component here. It comes for free. This is where I use the assumption that z is a set. So now I should just concentrate on finding an element in P of base. But this element of P of base will be given precisely if I prove this property. Because what I want, yes, P of base being this type here, and knowing that decode base of Z is loop Z, something that we already proved, we are reduced to prove this equation. So this is the only thing that is left to prove this equation. Okay, so final slide. We want to prove this equation for all Z. And here I have again a little bit of preliminaries. I need to prove this equation here. So let's prove it. Okay, so encode xp should be the same as transporting along x1 along p relative to x1 transporting 0. Ah, okay. So how do we prove this? Because we just need to do it again by path induction. So if we, well, okay, it's by path induction. So if P is ref, then you do some simple manipulations and you get it. Okay, so we have this property quite easily by path induction. Okay, so now we apply it to our problem. So if we instantiate it to our problem, we have that encode base loop Z is equal to transport x1 loop Z 0. I'm just instantiating it. But now I have another equality which is proved quite easily by induction on Z. Namely, that transporting loops along loop Z from 0 gives me Z. This is a consequence of the property that we had at the beginning, the fact that transporting along just loop, not loop Z, transporting along loop was to do +1. So if you transport now along loop repeated, well, you will do +1 repeated. And since you start from 0, you will get Z. So that's the reason why this holds. And hence, we have combined everything. So because of this, which we get by this nice correspondence between loop and the +1 function, we get this. This concatenated with this equality that comes from general reasons gives me this property, which was the final little piece which I needed to complete the proof of pi S1 is equal to Z. Okay, so now we change subject. Well, we are still in math, but we are not looking at the circle anymore. We are looking at another geometric picture, which is called the suspension. Okay, so the suspension can be represented more or less like this. So you have a space A, so topologically, you have a space A, which you can think of something like this, okay? And the idea is the suspension, so it's of dimension 2 because it's in the plane, okay? And I add 2 points outside in the space, one which I call the north and the other which I call the south. And then the idea is that I will draw, for each point in A, I will draw something called a meridian, okay? And I do this for all points of A. So in the end, the picture which I get is a kind of double cone. So this is now a 3-dimensional picture. So the space is entirely filled, okay? And it's a double cone because you have a north summit and a south summit. Okay, so this was more or less this circle here representing the border of A was more or less like the equator. Okay, this A was a kind of cutting the Earth in 2 halves. Okay, and the boundary of the 2 halves, and here I'm reconstructing the whole world by placing a North Pole and a South Pole. Okay, so now how do I do it in terms of type theory? By an inductive type, which looks a little bit like the circle. So instead of just requiring 1 point, well, first of all, it's a polymorphic construction, so it's not just a type. See, if you give me a type X in U, then you have a type, new type, which is called suspension of X. It has 2 constructors. Okay, so this is also there's a bad display. So you have 2 elements, 2 elements that you declare, 2 constructors, one which is called north and the other which is called south, that are both elements of sigma X. And then you postulate that for each element of X, so this was in the picture here, for each element of X, you postulate the existence of a meridian which is a path from north to south, just as drawn here. So these are the constructors. And then the induction operator is very similar to the induction operator for the circle. So if you want to define a function from the suspension, a dependent function from the suspension, you need to find a point in C at n, another point in C at south, okay? And again, the convention is that I have a capital N for the point in sigma X, okay, and small n for the point in the proper fiber of C, okay? So I have, the idea is that I have in my total space, I have, again, the image is the same. We want to find, here it's this picture, okay, the official picture, and I want to draw it inside C. And this is the formal north and south pole, and this is the real one in the total space of C. And then I also need, similarly to the circle, I need a proof that I need a proof that I need a path from N to S. Let's say it like this. I need to find a path from my little n to my little s for every X in X corresponding to every meridian. And because of transport, this requirement takes this shape here. Okay, and we have the axioms that go with it and which are natural. I don't comment too much. Okay, so we are going to do some work with these types. And before that, I need to do a little bit of preparations and to introduce something that is very important in topology. In topology, you have a lot of work that is done with something called pointed spaces. So in topology, a pointed space is a space together with a distinguished point in this space. Okay. So of course, for when defining contractibility, we already had this kind of requirement. But more generally, we are interested in the type U star, which I'm now defining as the type sigma XX. Okay, so it's a dependent type, and the underlying family of type is the identity from U to U. Okay, so if I want to write it in the usual way as sigma X Px for some family P, I will take this family, but because EUX by definition is lambda X applied to X, this is just X. So this expression makes sense. And this is U star. Okay, but an element, so the point is that an inhabitant of U star is a pair of a space and a point. And this point, we will use the notation star X for this distinguished point. Okay, and okay, and then of course the pointed space is this pair. Okay, but it's boring to always have it around. So we will also call X directly, the space without the star X, we will call it a pointed type itself, keeping this information implicit because otherwise it's a bit too heavy. Okay, so this is a notion. And then in mathematics, when you have a notion, you want to know what the morphisms are between these notions. So morphism of pointed types should be the maps from X to Y, which preserve the distinguished point. Okay, so now we have to do this type theoretically. So type theoretically, we are going to define this type of morphisms like this. Map star of XY is going to be by definition the pair of a function from X to Y plus a proof that it maps the distinguished point to the distinguished point. So because we are proof relevant, we need to give an explicit proof, and this is by propositional equality. And moreover, we can notice that we can also give a structure of pointed type to this new type by taking as distinguished point in this type the constant function that maps every element of X to the distinguished element of Y. So I call it star XY, and it will be the distinguished point of map star of XY. And okay, and another notation which I will use is that a typical element here will be denoted as a pair of a function and an element which I will always write star f, where this star f is the proof that f of star x is equal to star y, so star y. So this star f is my proof of this equality. Okay, and also the notation I will use, because this is again a bit heavy. So I will, to make it clear that f is a pointed map, I will add a little star here. So to say that I have a map from X to Y with a little star, X arrow star Y, means that it is a pointed map. Okay, and another notation will be this one. Okay, so next thing is to give you examples of pointed types. So there are two important examples, the suspension and the loop space. So the suspension of a type will be considered a pointed type by deciding, this is a bit arbitrary as decision, we decide that the distinguished point is the North Pole. So I'm sorry for you because you are South Americans, so maybe I should have chosen South Pole, but I follow the book because probably those people were North American when they decided that. And okay, so by deciding to take north as a distinguished point, then of course sigma A is always a pointed space. A little comment here. If A was, because these are all about pointed spaces. So when drawing this picture, I could have decided, well, from this picture, there was a better choice a priori for the distinguished point of sigma x. From this picture, I could just have chosen the distinguished point here, the one of A, okay? But the problem is that in this axiomatization, there is no way to say that x sits inside sigma of x. In this picture, of course, A looks like a subset of sigma x. But in this axiomatization, there is nothing like that. So I have no way to do this more neutral thing. So I have to be either North American or South American. And I decided, well, they decided to be North American. Okay, so this is for the sigma type. Sorry, for the suspension type. Yes, oh, the notation sigma is, of course, a bit confusing because it's the same sigma as for sigma types, but since you don't have a sigma x dot x column or something, there's no confusion possible. The second easy example of pointed type is when you take a pointed type A, then you can take the type of the equality type over star A, okay? And you have, in this type, you have a distinguished element, which is the reflexivity. So you define the type omega R to be this type. Okay, so omega R is called the loop space, okay, because it's really the space of loops. And it has a distinguished element, an obvious one, which is the reflexivity. Okay, so here is a theorem, which I'm not going to prove, but I'm going to state it. So for those who do category theory or who know a little bit of category, it says that suspension is left adjoint to loop space. So taking the loop space is right adjoint to taking the subset, the suspension. So it's one of the basic results in algebraic topology. So you find it quite early in textbooks. Well, maybe the ones which are more modern and more use more the language of category theory. So technically, it says that for any pointed space, for all pointed space A and B, there is an equivalence, and here I might, yes, there is an equivalence between, here I prefer to use my symbol, which is something like that, I don't remember, but okay, there is an equivalence between the pointed maps from suspension of A to B and the pointed maps from A to the loop space of B. Okay, so I don't think I will go through the proof, but I give you at least this hint that we don't prove directly that they are the same. We prove that both of them are equivalent to one reference type, the same type in both cases, which is this type. Okay. So I don't want to comment. If I don't give the proof, I don't. Yeah, I think it's. I might come back to it, but let me not go into it, just to be sure that I can cover the rest. And the proof of this fact relies on these properties that we have already used several times. Okay, so I'm not. There is a typo here again. Okay, so this is a proof, and let me just skip it. Okay, so I'm actually ahead of time, but maybe we can work on some exercises at the end, because I think that going through this proof will be just tiring, and let's not do it. So the rest of the final part of the talk is about something called fiber sequences. So it's related to these pointed spaces. Okay, and it's a very, very nice development. Okay, so let me start this, and since I have time, I will do it slowly, and I will essentially do no proofs. I didn't have time to write them anyway, and they are very well written in the hot book, so there's no real need to write them myself. Okay, so let's start this last part of the course. We are interested in sequences of two functions which are pointed to two pointed maps that can be composed. So f goes from x to y and g goes from y to z. And we say that this sequence is exact. Okay. I thought I forgot to write exact. We say that it forms an exact fiber sequence in the case that for all element y in capital Y, we have a correspondence, okay, which is an equivalence between two types. One which is inferred from G and the other which is inferred from F. So the one which is inferred from F I think something is wrong. Ah, no. Sorry. Yes, no. Yes. So it asserts the fact of being an exact sequence says that the two types related to F and G are equivalent. So the one related to G, because I start from Y, is the type of all Y's. No, the one which is, oh, sorry. Let me start again. So for each Y here, I will have, I repeat, this was correct. I will have two interesting types, one inferred by G and the other inferred by F. Okay. The one inferred by G is this type. It's a type of all equalities, all proofs of equalities that G of Y is equal to the distinguished element of Z. So in other words, it is, yes, okay. I cannot see it in another way. It's a set, well, it's a type of all proofs that G of Y is equal to star Z. The other one, related to F, is to take the fiber of F at Y. Okay, so maybe I repeat here. It's what is the fiber? It's sigma x x fx is equal to y. Okay, so if we were in a completely proof irrelevant world, what this would just say is that for y being in the inverse image of star Z, okay, so this is the notion of kernel, because if you think of star Z as being, now let's move to linear algebra. If you think of star Z as being the zero, then here we are describing the inverse image of zero. Hence, we are describing the kernel here. While here, okay, so sorry, if I just, I'm proof irrelevant, so I just want to know if this happens. So if this happens, it means exactly that Y is in the kernel. And if this happens, if this fiber is inhabited, if there is some guy X, that F of X is equal to Y, it is the same thing to say as saying that Y is in the image of S. Okay. So this isomorphism here is a proof relevant version of something that is more familiar from linear algebra, which is namely that Im of F is care of G. Okay, and if in another field of mathematics, which is called homological algebra, you consider sequences of linear maps that have this property, and you call them exact. So this notion that we are describing now is a proof relevant version, or if you prefer, higher structure version with some homotopical content of the notion of exactness that comes from linear algebra. Okay, so with these explanations in mind, what do we require? We require that for each Y we have an equivalence between these types. So it's polymorphic. Well, it's not polymorphic, but you have a family of equivalences. Okay, and moreover, you want these equivalences, these quasi-inverses, to be pointed in the sense, well, if, of course, before saying that it is pointed, I need to give a distinguished point in fib f of y. And the distinguished point is easy to find given the material that we have, because f is a pointed map. We have a proof. Okay, so remember that f being pointed means that I know that f of star x, oh la la, f of star x is equal to star y. Actually, that you have a proof of that, which I call star f. And hence, the pair formed by star X and star F is an inhabitant of fib F of Y. And I take it as distinguished element. And I want epsilon Y to preserve them. Okay, so this is the official definition of what an exact fiber sequence is. And now let's see what we can do with them. Before we do something with them, we are going to show that you have a lot of them. Here I see again a typo. We are going to show that, so this was about two functions, f and g. Now, if I just take one function, I can always produce from this function, I can always produce an exact short fiber sequence, namely this one. So I take f on the right, and on the left, I take as type here, I take the fiber of f over the distinguished element of y. Okay. And when you have a fiber, you always have a projection. Okay. Let me repeat again what fiber is. It's a sigma x of type x, such that f of x is equal to y. So it has as first component an element of x. So I can take the first projection and it goes to x. So here, this is a well-formed sequence of two functions. And theorem, it can be shown that it is exact. Okay, so that taking PR1 and F here, instead of F and G here, okay, so the role of G is played by F and the role of F is played by PR1, then this property holds for these instantiations. And it works. Okay, and as I said, I will not give the proof. Moreover, even if I don't need it in the proofs that follow, it's interesting to know that not only this is an example of exact short sequence, but it can be proved that all sequences like this are of this kind. So more precisely, every fiber sequence, okay, which now I have renamed it with Z, X, and Y, and G and F. So I renamed everything from here just to match the situation here. So what can be proved is that if I start, so this guy here is fixed, okay, but the theorem says that if I have an exact sequence with this particular f, but for some g, okay, then all these g's can be shown somehow equal to this special one here. And the situation here is very similar to what we did when we worked with the Grothendieck equivalence. So we had, remember, we had a type U over Y. Here again, there's a typo because the color is not the right one. Remember, we have this type, which played an important role at that time, and maybe I recall it. I recall this type. U over Y was the type sigma X of type U, X arrow Y. Okay, so it was the pair, the type of pairs of a type and a function from X to Y. And here you see that we have exactly the same kind of situation. We have our X fixed here. And by the way, our F also is fixed. And we want to plug onto it some function X that has X as a codomain, but this Z could be varying. So one possible choice is to take this choice for Z and PR1 for G, but there could be other choices. So you see that these pairs of a Z and a G, they vary in some type, which I write exactly in the same way as this one, but it is just a matter of taking into account the pointed aspects. Okay, so instead of having U here, now I have U star. Okay, so here there is also some typo. Okay, instead of U, I take U star, and yes, and instead of X arrow Y, I take the pointed version, which is map star of Vx. Okay, and then this is just alpha conversion. This V is the same as X here, up to alpha conversion. Okay, so the theorem says, which I'm not going to use, but it's nice to know that it exists. The theorem says that all the choices here that can exist to make an exact sequence turn to be equal in this type. Okay. Now, next thing is that we are going to produce not only a short sequence like this, not only a short sequence, but something called a long sequence. Okay, so that's the next step. Okay, so instead of starting with, well, no, just like here, we start with an F. So this is our basic construction. We start from F. And what we saw in this slide is that from F, we can build the beginning of a sequence, okay, with two morphisms. But then we could iterate this. We could consider now this as our basis and iterate, so take PR1 in the role of F and get another PR1 here relative to this F in other sense, in other words, we could take the fiber instead of taking it over PR1. So PR1 playing the role of F means that I will take now the fiber relative, the fiber of PR1, etc., etc. So this is what we are going to do. Okay, so this is the idea, to iterate this construction, saying that this is my new F, so I put something in front, etc., etc. So let's do this technically. So this is the last slightly difficult slide to follow, and the rest will, since I don't give the proof, the rest will be easy. So it's the last time for you to concentrate a little bit. Okay, so I'm going to define a sequence. My whole idea is to build. Let me give you the objective first. I want to build a sequence here, okay, which is infinite in this direction, where locally, if I take any two adjacent maps, the short sequence, which is just this portion of this infinite sequence, will be exact. Okay. And this is going to be the case by construction, because I will construct this family by induction by iterating this construction, which I know at each step gives me something that is exact. So the only thing I need to care about now is about finding the good notation to describe it. But otherwise, its existence is more or less intuitive and purely guaranteed by this theorem here, and the ID that we want to iterate. So for this, I need to rename things because this y here will stand as x0. So I call it x0. This x here will stand as x1. Okay, so I will rename it. X1 is now named x1. Sorry, x is now named x1. And then this initial f, which is here, I rename it as f0. Yeah, so I forgot to write f0 f. So this is another typo. Okay, and I also need to keep track of the distinguished points because I'm going to define later on. I will define x2, x3, f1, yes, f1, f2, etc. And each time I need to also take care of the distinguished point because all the maps that I'm going to build are pointed maps. So let me keep track of this at the beginning. Because x and y are pointed spaces, I take the first, so of course star n, so star here, maybe I put it here, star n will stand for the distinguished point in xn. So at the beginning for the x0, because x0 is y, I will take naturally the distinguished point of y as star 0. For 1, I will, because x1 is x, I will take the distinguished point of x. Okay, so this is the base of my induction. And now I need to find the proper definition for all n, larger or equal to 1. So all the f that will come later on will always be the first projection. All the xn plus 1 which will come will be fibers over the distinguished element. Okay, so you see that there's a difference of 2 here. N plus 1 refers to information at the level n minus 1. So this is the official definition of xn plus 1. These things are already known by induction. So you take as xn plus 1 the fiber for the fiber of the function fn n minus 1 at the distinguished point in xn minus 1. So just to make sure that we are not making mistakes, let me do this for 2, just to see that I'm on the right track. Okay, so x2, according to this definition, should be fib. And then, okay, so this is f0, because this was 2. So what is f0? It's f. So it's fib f. And then star n minus 1 is star 0. And what is star 0? It's star y. So am I on the right track? Yes, I am. Because this is the guy here in the construction that I want to iterate. So you see that at level 2, I'm just doing the first step of this construction. Okay, good. And then, okay, then it should sort of justify that this is the right definition because I'm doing this over and over. Okay, so let me erase this. And the subtle point, well, it's not subtle, is that I have to make sure that at each step I define properly what is the new distinguished point corresponding to the n plus 1 case. Okay, and it's going to be again an iteration. Remember that the pointed. Remember that we worked this out by giving to this type as distinguished element, we took exactly this pair here. Okay, so here you find exactly, so this, yeah, you, maybe I copy. Okay, and here I put it back. Well, it's a bit big, it's a bit too big. Yes. So you see that it has the same structure. The definition of star n plus 1 is star n, comma, star f n minus 1. And again, if I was to instantiate with n plus 1 equals 2, I would really get this. Okay, so this should explain why this notation works. And then I have explained this slide completely. So let me summarize. From this very basic data here of just two pointed types and a pointed map, I can build this infinite sequence, which is moreover exact. Okay, but it is not yet very satisfactory because I don't have any real information about what these guys are. What do they represent geometrically, etc. And here comes a magical dictionary. So if I just consider the first levels in this sequence, okay, so I stop at 4, just not to be too long, and I want to analyze this a bit more. Okay, so the first levels were x1 and x0, and here I restored, I reinstalled the original x and y and f. Okay, so this is my original f, but this is really x1, and this is really x0, and this is really f0. So now, theorem, and again, this is in the hot book. In this sequence that I have built somehow automatically without thinking too much, it happens that x3 is nothing else than the loop space of y. You can prove it. And x4 is nothing else than the loop space of x. Again, you can prove it. Actually, proving this automatically proves this, because here you have an interval of 1, 2, 3. Between them, you have an interval of 1, 2, 3, and here you have the same interval, and you know that this sequence is built exactly as this sequence, just starting a bit earlier. So it's actually enough to prove this. Okay. So this can be proved. As I said, I will not give proofs. Moreover, it can be shown that because now x3 is omega y and x4 is omega x, it can also be shown that the map here, which was defined as F3 in this inductive way, so F3 is some guy which is defined somehow mechanically, happens to be under these identifications. So if we take these equivalences seriously, we can match this F3 is the same as the map omega F up to these equivalences. So here I'm not very formal because well, we are all tired. Okay, so omega F is something that you imagine, but it's better to define it. So given an f from x to y, it induces what? So omega is a kind of functor. It induces a map from omega x to omega y. But we have to take a little bit care when defining it because we want it to be a pointed map. So we want omega f to map the distinguished point in x to the distinguished point in y, in omega x to the distinguished point in omega y. And also we need this to type check. So we need omega f to map some loop around the distinguished point of x. So it's a loop of type star x equals star x. It has to be mapped to a loop in star y equals star y. So if I just apply functorially this f is a map from x to y. So f, and this was my p here. If I do f of p, it doesn't have the right type because f of p will have the type f of star x equal f of star y. And this is not what I want because I want it to live in this type, which is this type. Hence, I need to adjust. But remember that I have star f, which is precisely a path from f star x to star y. And then if I concatenate the other way around, I have here star y. And so by concatenating fp with star f on the right and star f minus 1 on the left, I get something of the right type. So this is the official definition of omega f. Okay. And hence we have a map here. And so the theorem is, summarizing it, x3 is the same thing as omega y, x4 is the same thing as omega x, and f3 is the same thing as omega f. Hence, our sequence here, which is a bit like formal or, well, category theorists often call these kind of arguments abstract nonsense because it's purely formal, becomes something much more interesting, which is this sequence now looks like this. So this x2, I call it z, okay? So this part of the sequence is now this one, zxy, but then it's, instead of x3, I have omega y, instead of x4, I have omega x, and then it's easy to see that iterating the thing, starting just from here, this guy, I can call it omega z, and then starting all over again with respect to this guy, because I have a distance 3 here, 1, 2, 3, yes, this guy is omega 2y, etc. And this sequence is very well known in the most modern topology books. I think you need to go to the books like in the 2000s, because in earlier topology books, you find another sequence, which I'm going to discuss now. So this is called the long exact fiber sequence, okay? And it's a sequence of spaces. Okay, in topology, instead of types, you speak of spaces. And these are called the loop spaces, and these are called the iterated loop spaces. Okay.
Excuse me, that is a raised hand.
Yes, yes. So please go on.
Yes. It seems like somehow you can just assume the function is a vibration, right? Because the usual long exact sequence here, you need to do some trick about replacing your function with a vibration or something like that. like otherwise you cannot use the fiber of the function. You have to use some homotopy fiber thing, and it seems like in here you don't need to do any of that.
No, you do. No, I think yes. The type theoretic setting tells you that you can look at it as a fibration directly, and in other words, remember the work we did with Grothendieck correspondence, or Grothendieck equivalence. In the classical Grothendieck setting, it says that a fibration is the same thing as a pseudo functor into cat or something like that. So it's again, you see that in the types in the categorical setting, you need to have the setting of fibrations. But here, because everything is encapsulated in the higher dimensions that is hidden in the identity types behind, everything works just by saying, I just have a map from X to Y, and it contains all the information. It's a bit magical, but it works.
Okay, great, thanks.
Okay, so next thing, which I want to do, and I think this is the final thing, I want to show you another sequence that is more familiar in older textbooks and also modern textbooks. But before this long exact sequence attracted the attention of mathematicians, there was another one which was known much earlier. So I don't know exactly the history, but these business of iterated loop spaces, I think, goes back to the history of operades. And well, it's quite old. It's from the 1970s. So I would guess that this presentation, this notion here, is due to people who invented operades like Peter May. And this is probably in the 70s, I guess it. And long before that, well, maybe in the 50s, or I don't know exactly, but long before that, algebraic topologists had recognized another exact sequence, which involves not explicitly spaces, but, well, it does not involve spaces, but only groups. Okay, so there is an exact sequence which is involving something called the homotopy groups of a space. And it has exactly the same flavor, okay? But instead of being a sequence of spaces, now it's a sequence of groups, okay? So we are back to something that is more like a group theory than topology, okay? And this is why, by the way, there's a branch called algebraic topology, where you try to approach topological problems through algebra. Okay. So the question is, can we account for this other more ancient, more older sequence using the language of homotopy type theory? And the answer is, we cannot do it with the tools that I have introduced so far. So I'm not going to start a new lecture because we are 6 minutes before the end, but I have just one slide to introduce to you another ingredient, which is more or less the last important ingredient that you can find in the hot book. Well, there are others which I'm not super familiar with, but I would say that this is the main one that is missing if you want to have a more or less complete picture of at least the most important things. We need something called truncation. Okay, so let me introduce truncation. And you see, this is really the final slide. So before I introduce truncation, let me tell you why this is relevant here. It happens that in type theory, in order to define these homotopy groups, Okay, maybe I should define what are the homotopy groups for an algebraic topologist. So if I have a space A, then pi n of A, sorry, a space with a distinguished point, pi n of A star is the space of all maps from Sn to A up to homotopy. Yes. Yes. Okay. So it's supposed to be based maps, but let's not go into too much detail. So you see that for the first group we really have what we wanted, because S1 is just like the equality type as we have as no. Okay. Something. No, but that's true. Ah, no, sorry. It's a looped. Okay, sorry. Here I'm a bit too tired. Here is the definition here. So I will first introduce the notion. The notion of truncation can be done at each H level. So the idea is that, well, it's a philosophical idea. In some sense, homotopy type theory forces you all the way to consider that the structures you are manipulating, the types that you are manipulating, they carry with themselves a whole higher structure. You cannot do anything about it because because of the identity types, you have this. And you have a nice theorem proved by several people, which says that in type theory, in homotopy type theory, every type is equipped with an infinity groupoid structure, whatever this means. So sometimes you just want to be down to earth. You just want to manipulate A as if it was a set or a groupoid, but not a very fancy N groupoid. So of course we have introduced tools for that. We have said, when can we say that a type is like this? But we want an explicit coercion. We want sometimes to say that from an arbitrary type, we can get one associated with A, which has a specific H level. So we want to do a truncation of A at some level. Okay. So if we put here an N equals -1, it will mean the propositional truncation. If we put here an N equals 0, it will mean the set truncation, etc. And how do we define it? Again, by means of something that looks similar to all what we have done. So we will first form this type, then we will give constructors, and constructors are given by each element of A gives rise to an element of the truncation. Okay. An inhabitant of A will be an inhabitant of the truncation, because an inhabitant of A is just the first level of an element of A is of a dimension, low dimension, so to say. So you will have a function that maps A to its truncation, and then you will have this principle that cannot be called an induction principle, but has a little bit the same flavor. If you have a type family where you are sure that all PXs are N types, so you are guaranteed that they have not too much higher structure. Their higher structure stops at N. Then, in order to build a function from the truncation to this family, a dependent function, it's enough to define an ordinary function, dependent function from A. And then you have a definitional equality that goes with it. So if you apply this new function to the coercion from X to the truncation, it's the same as applying this original function f to A. And thanks to the truncation, we can now define these homotopy groups, which I defined in a sloppy way. Just forget it because I was a bit tired. The official definition of the homotopy group is to take the iterated loop space, okay, and to take its truncation at 0. And hence, we have now a formal way to connect this sequence to this sequence. So we have to apply truncation all the way to the sequence, and then we need, of course, to work out how we work type theoretically with this truncation, and this would take 1 more hour or 2 more hours to do this properly. But I wanted to stop here just to explain you that this truncation business will become important when you want to prove down to earth all style property. If you want to do fancy mathematics that deals all the way with higher dimensional things, then you don't need too much truncations. But if you want to do all style things, like speaking about just groups that are not groupoids, etc., then you will need truncations. Okay, that's the end of my talk. So I hope that you've seen enough of homotopy type theory to get a feeling. Okay.